Hello everyone, my name is McKenna Worley. I'm a graduating senior from Westminster University, class of 2026. This is my capstone project for the computer science and data science departments here at Westminster. Probabilistic, ancestral inference, reconstructing the unknown.
Before diving in, let's talk about the problem. I worked with stochastic data, which involves random probability where future and past states cannot be precisely determined. A real-world example of this is genetics.
So the reason why I chose to work with DNA is because it follows strict Mendelian inheritance, like your Punnett squares from high school, but these models assume we know the parent. In reality, we often don't. So instead of predicting forward or down the family tree for children, I wanted to work backwards, going up the tree for ancestors. That's the broader idea behind this project. I think of it as algorithmic archaeology, using what we know now to infer and mathematically prove what happened before. To explore this, I built a full-stack application that simulates genetic data and attempts to reconstruct individuals in the family tree. The system uses msprime to realistically generate my data with family trees and different allele combinations, or Punnett squares. What you do is, as soon as you land on this page, you can select a dataset. We'll choose public. In here, you can see the dataset dashboard. It'll tell you a little bit about what it is. You can see that green means the data is known. Red means the data is missing. Here, we can see that this individual right here is completely missing. You can page through. You can also download this dataset if you want to. Below this, you can see the family tree. So if we want to select an individual, we can actually see this individual's parents, the individual itself, and the children below. If we come up here, we can choose a model. I'll just choose this deep neural network. If we scroll past this, we can see a little bit about the data set, so the model size, a little bit about the model strengths, what's best for. If I change to our best model, which is the Bayesian inference, you can see a little bit about the data, so it's a lot smaller. We can see how the model was trained, a little bit about this model, strengths, weaknesses, and if we actually want to test the data set public on the selected model, Bayesian inference, actually run that data, it's actually applying that model in real time. So right here, we can see that the tiny model was applied to this data set. You can see the accuracy, the balanced accuracy, and all these other statistics here. A little bit about how these numbers actually mean, and some graphs to show what's going on. If the graph is too small, you can actually click on it and it'll pop up a lot bigger. A little bit about how these graphs work and what they mean, and then you can actually see every single error that exists. So there were in this data set 1,817 errors. You can also turn on dark mode. With dark mode, it actually flips the graphs. So the graphs are actually with a dark background so you won't get flashbanged. If you want to, you can open the side menu. You can create a data set. So if I want to make a data set, I can name this video demo. So I just made a data set. And then if I see right here, I go up to the top and see the video demos data set. You can find this project at capstone.mckennaworley.com.